Hi everyone, welcome to this video presentation of our ICCV2025 work, IFAdapter. Although current text-to-video generation models have become remarkably powerful, they still struggle with spatial accuracy. For example, imagine that a layout in your mind like one shown on the left. You want to generate a vase with 3 flowers, one purple with a white center, one pink with a yellow center, and so on. But here's the problem. How do you craft a prompt that allows the model to generate exactly what you want in your mind? That's nearly impossible. Sure, you could try writing a very detailed prompt, but the result, as shown on the right, often has major issues. Wrong number of flowers, incorrect precision, inconsistent attributes, and more. This illustrates a key challenge in controllable image generation. Even with the elaborate prompts, models still struggle to faithfully reproduce the user intent in spatial grounded scenes. To address the issue of spatial errors, the layout to image task was introduced. Instead of relying solely on the ambiguous natural language prompts, this task allows users to provide an explicit spatial layout, a visual guide that defines what objects should appear and exactly where they should be placed in the scene. This structured conditioning offers a more precise way to control the generation process and greatly reduce the chance of error in object count, position, and appearance. One of the most representative work in layout-to-image generation is the collision. As shown in the left image, the process starts by encoding each object instance using the diffusion model's text encoder, a clip model, to obtain semantic embeddings. These embeddings are then combined with the corresponding bounding box to form grading tokens, which encode both what the object is and where it should appear. Collision introduces a trainable self-attention layer and blind these grounding tokens with the orange image tokens. However, one major limitation of existing models is that the description for each instance are often very short, typically just the object category. For example, a layout might simply specify a fork or a cup without including any rich attributes or other words. As a result, the model lacks fine-grained guidance for appearance detail like color, material, or style, making it hard to generate diverse or realistic instances. So what happens if we try to include more complex, detailed description for each instance? And here's an example. Here's a slightly more challenging example, and unfortunately, existing methods completely failed. As the demand for fine-grained, high-quality image generation continue to grow, this limitation becomes a serious bottleneck for real-world application. To tackle the problem of missing instance level details, we identify two key root causes. The first reason lies in the training data itself. As the saying goes, you are what you eat, and models are no exception. Most existing layout-to-image methods are trained on datasets that contain only the simple category labels and a few basic attributes. So what's the solution? The idea is very simple. Let's build a new dataset that actually contains detailed description for each instance. Especially, we start by using grounding dino, an open-set object detector, to identify all the entities in an image and extract their bounding box. And now we have a high-quality dataset. What's next? Let's revisit the collisions and take a closer look at how they encode instance level information. Interestingly, for each instance, collision only uses a single token. specifically the end-of-text EOT tokens for the text encoder. Due to the contrastive training objectives, the EOT token is good at capturing coarse semantic meanings. However, it largely ignores fine-grained details. As a result, relying solely on the EOT tokens for instance encoding inevitably lead to the loss of important visual attributes, such as color, shape, and texture. A straightforward, or rather naive, solution will be to replace the EOT tokens with all 77 text encoder tokens from the original prompt. While this might seem reasonable at first, they introduce a serious practical problem. Imagine that generating an image with 10 instances, if you use 77 tokens for each instance, and each token needs to attend to the image via cross attention, then the memory and compute requirements will scale almost linearly with the number of instances, making it as inexpensive as running 10 full text-to-image models in parallel. In practice, this becomes infeasible to train, especially on high-resolution images of large bench size. Moreover, many of those 77 tokens are actually padding tokens and do not carry any meaningful information. So, not only is the method inefficient, it is also wasteful. To solve both of these two issues, we introduce resampler models. Specifically, we define a set of learnable carriers which interact with the no padding tokens in the original text use cross attention. The output is a small number of fixed length appearance tokens, which effectively summarize the visual detail of the instance. This design elegantly addresses both problems. First, they avoid the overhead of processing all 77 tokens per instance. And the second, they remove redundant information by focusing only on the meaningful parts of the input. Finally, we combine the EOT tokens with the newly generated appearance token to form a richer instance representation. This combined guidance is then injected into the generation process, allow the model to follow both the core semantics and the fine-grained visual details of each instance. In this way, the model benefits from the generalization power of the EOT tokens, while also capturing the nuanced appearance features provided by the resampler tokens, the appearance token. There's also another foundational limitation in existing methods. They typically rely on grounding tokens, which are represented as 1D token sequence. However, these tokens are used to control generation on 2D image plane, yet they contain no explicitly spatial priors. This mismatch makes it harder for the model to understand where objects should appear and often leading to the incorrect placement or overlaps, especially in complex scenes. To address the lack of spatial priors, we introduce a 2D map-based guidance mechanism. The idea is to generate a feature map for each instance by performing cross-attention between the appearance tokens and the image tokens. To enforce the spatial priors, we restrict each instance to only attend to this corresponding region in the image. This introduces strong spatial priors into the attention process. Finally, to avoid the feature conflicts in overlapping regions, we apply a weighty feature blending strategy to combine all instant maps into a single global guidance map. This final map serves as the overall conditioning input to guide the generation process with both fine-grained details and the spatial process. With our proposed method, we achieve precise control over both object positioning and visual details, As shown in this example, our method significantly outperforms previous approaches, especially in generating high-frequency details. For instance, we are able to faithfully render complex visual elements such as the red duals with yellow stars, and traditional ink paintings or the color-blocked floor, which are typically challenging for other methods. In addition, the overall image quality produced by our method is noticeably better, with more consistent structure, clear texture, and fewer artifacts. Our methods excel at generating complex colors and challenging materials, where previous methods often struggled. For example, we successfully generate the scene's contents of bronze horse, a wooden flower pot, and something else, all of which involved intricate texture and subtle material cues. Perhaps most impressively, when they come to high detail texture, which are difficult to reproduce, our method delivers visible superior results, capture both the fine-grained patterns and the realistic surface property. Our quantitative experiments also confirm the effectiveness of our methods. Across the multiple benchmarks, we achieved state-of-the-art performance in terms of region-level fidelity and fine-grained controllability. Whether this object placement accuracy, attribute consistency, or visual realism, our method consistently outperforms previous models, showing this strength in both precision and quality. That's all for my presentation. Thanks you very much for watching.